He received his PhD from Harvard University in physics and was a postdoctoral scholar at Caltech prior to his appointment at Maryland. His research themes range from quantum electromechanical phenomena such as Casimir force to fundamental solar energy conversion process with an emphasis on optics, photonics, and thermodynamics of such systems. He is a recipient of the NSF Career Award, the Weiner Young Investigator Program Award, the DARPA Young Faculty Award, the USA Adolph Lom Medal, the IEEE Photonic Society Young Investigator Award, the SPI Early Career Achievement Award, and the NASA Early Career Faculty Space Technology Research Award. I never came across someone with so many awards at such young age. Welcome, Professor Munday.
Great, thank you so much. Great to be here today. Can people hear me? Over there. Sure. I've actually got 3 mics. I have 2 here and 1 here, so now I think we're all set. All right, well, thanks again for having me today. It's a pleasure being here. So I'm going to talk to you about some different types of what I call photonic technology, so different things that we can do with photons. So before we get too far into that, I'd like to just discuss, what is a photon? Now that might sound like a kind of trivial question, but it's kind of an interesting one. And photons and photonic technology are very important to us, as we know from all of telecommunications and whatnot. Also, even this year's Nobel Prize went for things related to laser physics, so again, using photons. But I'd like to ask a more deep question, maybe about what fundamentally is a photon. At least starting out, let's think about that. So we can ask another Nobel Prize winner who got his prize for looking at quantum optics and having laying down some of the fundamental groundwork for that. And if you ask him this question, this is what his response is. A photon is the thing that makes a photodetector click. Okay, I'll take that. I mean, that's great. And if you think about it, I think it's a great response because it's kind of it's simple, but it's also kind of deep. And so I'm actually not going to go any further. This is as much as I'm going to get into about what a photon actually is. I'm rather going to focus on what we can do with photons. And so we can make a photon detector go click. Well, what else can we do? Well, can we, for example, make an IR photon click using a photodetector that's made of silicon? So for example, silicon, it absorbs visible light very well, but it doesn't absorb IR light. So can you make silicon absorb or go click if you are using IR or near IR photons? Another question that I would like to ask is, can we push around an object the size of a building using photons? So photons, it turns out, they exert a pressure. It's a very small force, but can we use that to propel an object that's very large? Another question is, what if we're in the dark and we don't have any photons? Does the very fact that photons could exist, can that be used in some way? It turns out that there's actually forces that exist in vacuum as a result of just the fact that photons could be there, even though they're not actually there. So I've broken this down into 3 parts. First part, I'll talk about some optoelectronics and things that we can do with light absorption and what I'll call hot carriers. Then I'll talk about how we can mold the flow of light in certain structures electrically. And then finally, I'll talk about what we can do with photons when they're not home. All right, so starting off, there's a picture here of some stained glass. Does anybody recognize where this picture might be? I think I heard the answer. Sagrada Familia. It's very good, thank you. So this is a great cathedral that's been in preparation for a long time, as you see down here, from Gaudi. But the idea here is that you have stained glass, which can have all these beautiful colors going from blue through red, that's related to scattering of little nanoparticles that are made out of different metals. And by having different sizes and different types of metals, you get all these different colors. And so this is sometimes referred to as plasmonics, the way that light couples to these small metal particles. So this can range all these different colors. There's something else that people sometimes refer to as plasmonics. These biscuits, I don't know if anybody's seen these before. So I once shared an office with an Italian postdoc that told me that this is what plasmons are. He also knew a whole lot about the other plasmons as well, but I just thought it was interesting because I hadn't seen this before. But moving on, so what really are surface plasmons? Well, if you take light, so electromagnetic radiation, it comes down and it interacts with a small metal particle. The light can couple to those free electrons and start jostling back and forth. And that's what you see here in this small particle. We call these localized surface plasmons because they're localized attached to this little particle. We can also have propagating surface plasmons. So this is if you have light that comes down onto a metal surface, and if it can couple to these charges, it can then propagate along the surface. And the thing that's interesting about this is you can have very high field intensities near these metals. So if you want to concentrate a lot of light into a very small region of space, this is a good way to do that. However, well, I guess first I'll say that can be used for a variety of things. You can think about for photovoltaics, for example, if you want to concentrate a lot of light near a semiconductor so you can absorb it. However, there are also drawbacks, and specifically you have strong optical loss. So in addition to getting the high fields and absorption in the semiconductor, the metal will absorb a little bit of that light as well, and that's usually a bad thing. And so what we were wondering is, can we take advantage of that optical loss that occurs in the metal for something useful? And so here's an example of that. So what I'm showing you now is there's a 3-layer structure. So the TCO, that's a transparent conducting oxide, something like indium tin oxide, for example. A thin insulating layer, usually a few nanometers of a dielectric, in this case aluminum oxide, and then another metal here. So you can think about this kind of like a metal insulator metal sort of stack. And if we shine light from the left here, the light will go right through these first 2 layers because they're both transparent. Now, on the back side here, if we can either structure this metal or we choose an appropriate thickness, we can actually have a lot of that light absorbed in the metal, but not in any of the other parts of the structure. And so when we do that, that light transfers its energy here to the electrons. So you end up having electrons that have a lot of extra energy, and now they have enough energy that they can jump over this little insulating barrier. And so you could hook this up to a load, and you could use this for either energy conversion, if you'd like, or you could use it for photo detection or something like that. And so these carriers here that have this extra energy, we sometimes refer to them as hot carriers, hot electrons. That's because they have more energy than an electron normally would in equilibrium conditions. All right, so we've made a few different types of devices out of this. So here's a little schematic of one, where the top layer here, so I've got indium tin oxide, again, as I showed before, aluminum oxide here, and then aluminum at the bottom. And so right in this intersection here, you'll see that that's where the device is, where you've got this metal insulator, metal structure. And so aluminum is nice because it's abundant and low cost. It's a material that you can use for plasmonics. It's very good to kind of tune throughout the visible spectrum. For us, what was really important here with the aluminum oxide, or with using aluminum, is that we can get a natural aluminum oxide layer very easily because we can oxidize it. So previously we were using other processes to put down thin insulators, but they would oftentimes have a lot of holes, meaning physical voids in the deposition process, and so then you'd have shorts and things like that. So aluminum worked pretty well for these things. One of the disadvantages, though, is we don't get a lot of absorption. So here is looking at the absorption in the structure, and if we break down the amount of absorption we get in the aluminum, which is good, we want that. There's a little bit of absorption in the indium tin oxide, which we don't want, but it's still there. But it's the difference in these absorptions that's really important. So it's relatively flat across here, so it works for a wide range of wavelengths, but it's not very large amount of absorption, less than 30%. So this is what the absorption looks like. We turned these into devices, and we looked at what the photo response is. So this is the amount of current per unit input power. And we see, as a function of wavelength, we get a peak here in the blue. And so it works fairly well there. But it's not broadband like you would expect from the absorption. And that's simply because the blue photons have a lot of energy, so they can easily jump over that barrier. Whereas these red photons over here, they don't have enough energy, so even if you absorb, if they get absorbed, they're not going to generate carriers for you. So now we can absorb some light, we can generate photocurrent, but we're kind of limited to this blue response. And what we'd like to be able to do is to tune it to other wavelengths. And so this is where we can take advantage of this concept of plasmonics that I talked about earlier. So here's a similar sort of structure. It's another planar one. We get kind of uniform absorption across the visible range here. However, if we incorporate some nanowire metallic structures to it, we could end up having a lot more absorption at specified wavelengths. So in this case, we got something around 800 nanometers to be absorbed very significantly here by tuning the properties of this. And basically, you're looking at the changing the periodicity between these and the size of these diameters, allowing you to get a lot of absorption in this thin aluminum layer. And there are other ways you can tune this as well. So this is tuning the geometry with a particular metal. You can also look at different types of metals, and then what happens in that case is this, the density of electronic states that can exist can vary from material to material, and that's also important in trying to design these devices. So there's a number of different types of materials you could also use. But we're still limited now that we've got one single wavelength. And also this is a lot more complicated. We now have nanowires that we're trying to align and put in here, and it's only this one wavelength. So we'd like to make something that is simple and also very broadband. And so simple, one thing's very simple are thin films. So here's a picture that you could have taken from a parking lot after a rainy day, which you don't have a lot of here. But you could have some, there's a little bit of oil on the ground, you get some water in there, and so you've got this layer where you've got water and oil on here. And then you get interference conditions, which can give you pretty pictures, even though it's kind of a nasty thing, the oil and water mixture. It looks nice. And so this is a very common phenomenon, right? So you're just looking at thin film interference in a dielectric slab. And so this is what's used a lot of times for anti-reflection coatings, right? So you put on a thin dielectric layer, there's very little loss in that layer. And so what happens is basically you've got light that gets reflected off this top part, and then some light goes all the way down and gets reflected off the bottom part. And when they come back, you look at the phase conditions that occur between them. So you can either have constructive or destructive interference. And so if you choose the appropriate interference condition, you can have light either pass through or be reflected. And that's how it works with dielectric thin films. And these film thicknesses are usually on the order of a couple hundred nanometers, because you want it to be some fraction of the wavelength of the incident light. And that's, again, for a low loss dielectric film. So it turns out, if you use a lossy dielectric film, it's actually a little bit more interesting. So here's some work that came out a few years ago where they looked at very thin lossy films. And so now when you look at the phase that's accumulated as you go through, in the bottom one here, the amount of phase that you pick up is dramatically different because you now have loss incorporated as well. And so in this case, you can actually have films. These are germanium films here on top of the metal substrate that are on the order of 10 nanometers or less, so about 100, or a factor of 10 or so less than traditional films, and you still get these vibrant different colors out of this because it's a lossy film now, and the interference conditions have changed. And so what we were wondering is, could we do that with a metal? So could we make a thin film metal that absorbs a lot of the light? And so your first instinct might be, well, if I take a piece of silicon and I put a layer of metal on it, it's not going to absorb much. It's actually going to be a good mirror. That's kind of how we make mirrors usually, right? And you'd be right in that assessment. So if you look at this, if you look at the absorption, now I'm looking just past the band gap of silicon, so into the near IR. There's this solid line here which is a calculation of what you expect the absorption to be in that metal. And here's some circles showing what the experiment is. And it's exactly what you'd expect. It reflects most of the light back when you have a film that's on the order of, say, 20 millimeters. And another way to think about that is, as the light is coming down, there's a large index contrast. And if you have a large index contrast or an impedance mismatch, you get a lot of reflection. So that's what you see. However, if you flip it over, and we can put a nice traditional anti-reflection coating on top here so we get the light coming into the silicon absorbs visible light, but this is beyond the visible, so it's not going to absorb any of this light. Then it can go down to the metal, and we want to see what happens in that case. And so in that case, we actually get more than 70% absorption in the thin metal film. And so this is a thin metal film that's on the order of, like I said, 20 nanometers or less, and the wavelength of the light is over a micron. So we've got like a factor of 100 times thinner of this metal film, and it's absorbing a ton of the light there. And so it turns out that this was actually observed. There's a simple expression for this, where you can relate the index of the top material and the bottom material. So the top material in this case is silicon, bottom would be air, and then you've got your metal here. And the maximum absorption you can find from a ratio of these quantities of the index. This was pointed out actually back in the 1950s under a completely different wavelength regime, but it's a very interesting effect that was kind of rediscovered several decades later in the 2000s. So we said now that we can do this, at least in principle, what kind of optical properties do we need of our metals? And so it turns out that we need to have the index of refraction, the real part and the imaginary part, so N and K, to be approximately equal to each other for this metal, and we want them to be relatively large. So are there metals that would do that? And so the plot here, we have on the left axis, we have the imaginary part of the refractive index. The bottom part, we have the real part of the refractive index. We said, let's suppose that the metal could have any value we want. Let's just calculate and see how much absorption would be possible. And so as that simple expression showed, we can get above 70%, so almost 80%, in this region right here, where we have, again, kind of N and K are equal to each other, and they're relatively large, on the order of, say, 5 or 6. Okay, so why haven't people seen that? Looking at plasmonics, it's been a pretty hot field for the last decade or two. Well, it turns out that most of the metals that people use lie over here. So silver, gold, copper, aluminum, they're all over here, where the imaginary part is relatively large, but the real part is relatively small. So in that case, you're only going to get absorption on the order of, say, 10, 20, maybe 30%. However, if you start looking at some of these other metals, we see that we can get above 70, close to 80% absorption on them. So that's what we went to look for. So we took 3 of them, so platinum, iron, chrome, and titanium, and we looked at what the absorption would be. So these are calculations here. We've got some experiments on the next page. But we're curious, as you vary the thickness here, how much absorption can you get? And so I'll just take this first one here with platinum. We see for 15 nanometers of platinum, we can get over 70% absorption in only a 15 nanometer thick layer of film. So 15 nanometers of film, and again, this is above 70% absorption over this near IR frequency range. And so then we did this experiment. And so the other thing that's interesting here is you can see that it really is an interference effect that you're observing, because if you start off, say, with a 10 nanometer thick film, so it's too thin, you get some amount of absorption. You make the film a little bit thicker, you maximize your absorption, and then as you make it thicker, it absorbs less. So if it was just normal kind of exponential absorption, you'd say, well, you just make it as thick as possible and you'll absorb a lot, but that's not the case here. You actually want it to be very thin to get the right amount of absorption. And then on the right, we have the calculations showing the between. Okay, so we can get a lot of absorption in thin film. The next question is, can we use that absorption to generate hot carriers and collect a current? And so in this case, it's a similar sort of structure we had before, but now we're using a semiconductor and a metal. The light comes through, and at this wavelength range, again, the silicon is transparent. We absorb the light in this thin metal. We generate carriers that have this extra energy that can then jump into the silicon. And so we make one of these detectors, and we compare it to a traditional silicon detector. Because the idea here is that we'd like to be able to use this in a silicon-based platform and not have to worry about like wafer bonding with 3,5 material or something else. We're going to stick strictly to silicon. And so we compare it to a silicon detector here. We can see that near the band gap of the silicon, so at around 1.1 eV or about 1.1 microns, we end up getting that the silicon detector works better, as you would probably expect. But as you go to longer wavelengths here, to the near IR, we get a couple of orders of magnitude better response out of this thin metal device. So we wanted to use that to try to image something. And so here's an example. Here's an optical image of basically it's just a glass slide that has a metallic circle that's been made on it just for imaging. Nothing special about that circle. And then we take an image with 2 different scanning detectors. So the top one here is this hot carrier detector, zoomed in on this region here. And the bottom one is this commercial silicon detector. So the silicon detector works better near the band gap. But as we go to longer wavelengths, we start to see that the response is better for this hot carrier detector. As we go to longer and longer wavelengths, we see that the silicon detector stops working, but this hot carrier detector continues to work well. So this is one way that you can start to think about making devices and detectors on silicon without having to resort to other types of materials. All right, so before I switch gears and go to the next topic, I just wanted to say a couple of other fun things that we can do with optoelectronics and thinking about photons. So here's an example of where we take a single semiconductor. So in this case, we're using gallium arsenide. And then we're modifying the optics around this material. So putting materials that will block the flow of light into or out of it. And by doing that, we can actually change the output color. So in this case, we're kind of shifting from 1.4 to about 1.6 UV in output, the peak output intensity. We can also incorporate this into a photovoltaic device. We see that we increase the open circuit voltage. And we can also use this to control the flow of the dark current in these devices, just by modifying the optics, not any of the electronics. We're also looking at ways to modify the thermal emission. So if you think of thermal radiation, it's basically it's light, it's really long wavelength light. And so if you have a solar cell and you can modify how much of that thermal light that gets emitted, you can actually cool it down and make it more efficient. And also thinking about solar, another thing that we've been thinking about is ways in which you can use something that's kind of like a photovoltaic device, but that would work at night rather than during the day. And that might sound kind of counterintuitive at first, right? Because if it's a solar cell, it shouldn't really work when there's no sun. But here's how you can think about that. If you have a normal heat engine, you've got a hot object and a cold object, and heat will flow from one to the other, right? And so a solar cell is kind of like that. You've got the hot object, which is the sun, and the cold object here is our solar cell. And the mechanism by which it does it is the photovoltaic effect, but you can think about it just as exchanging energy or extracting energy from two different temperatures. So the way that could work is you could flip this around, where the solar cell now is the hot thing, and the hot thing being kind of what we consider room temperature, and the cold thing being the night sky. So deep space is actually very, very cold. So if you can interact just with deep space, that can be your cold body, and the Earth can be your warm body, and you have kind of a reverse photovoltaic effect, where basically all the currents and voltages get flipped, but the output power is still positive. So there's a lot of fun stuff you can do with light and photonics in the field of optoelectronics in general. All right, so now what I'd like to talk a little bit about is how we can control the flow of light electrically. So using voltages in order to modulate where the light is going. And so one motivation that we had for thinking about this was looking at the energy and power consumption you have from buildings. So about 40% of the total US power consumption is from residential and commercial buildings. And if you break that down further, what you find is that heating, lighting, and cooling, that makes up about 40% of that. So it's a lot of energy being consumed in those things. And so if you think about a building, windows really kind of windows are your kind of input and output where energy is flowing in and out of that building a lot of times. Because you've got heat flowing in or out, you've got light flowing in or out. And so if you could start to modulate these windows, you could try to generate power from them, you could modify the amount of light coming in or out, and you can also think of having thermal control. And so smart windows, as they're sometimes called, they do exist, and most of them have a variety of different limitations. So here's a commercial option that is available right now. These are electrochromic materials. You might see them on jets sometimes when you're flying, and they can basically go from a transparent state to an absorptive dark state. There's also polarized liquid crystals. So this is, you basically take cross polarizers and you put a liquid crystal film between it, and you can either let half the light pass through on the left here, or you can have none of the light pass through when it's absorbing. And then if you want to try to generate power, there are semi-transparent solar cells. So these are not generally active, where you can't change the way that light is flowing into or out of them, but you can generate some power out of them. So these are some of the available options. Now the pros, at least for the ones on the left, is that you can control the external, the amount of light that passes through. And there's also some control of heating. But in general, they don't allow you to produce power. In fact, they consume power when you're doing that. They're absorbative, especially in these two cases, which means you're actually losing energy because you're absorbing it and it's just being dissipated as heat in that window. And there's also no glare control. So for me, I know, like in my office, I've got a window. I like to keep the window open, let the light in, but sometimes I'll start getting glare off my monitor. So what I'd really like is to have the ability to make that light scattering and diffuse rather than just coming in and giving me glare. So that would be another kind of added bonus if we could do that. And so we'd like to have these pros without some of the cons. And so the method that we've been using is something called a polymer dispersed liquid crystal. And that works in the following way. So you can see right here, this is what one of these looks like. There's a polymer, and there's little droplets of liquid crystal that are inside there. And the nice thing about using this is we don't have to use polarizers anymore. So what happens is the light comes in, and as the light comes in, it sees the index of refraction for this polymer, and then it sees an index of refraction for all of these little liquid crystal droplets. And because there's an index contrast, the light starts to get bent and scattered. And so then what happens is the light scatters all around, and then it looks white, like you see here. So it looks kind of like white paint or something. Now, if we apply a voltage to it, now what happens? Actually, before I show that, this is what one of these looks like in an SEM. So these are little droplets. They're about 1 or 2 microns, usually. And so if we apply a voltage across it, now this liquid crystal starts to align. And for any of the light that's coming in, we've chosen the liquid crystal in the polymer such that there's no index of refraction contrast as the light starts entering in when it's all aligned. So that means that it will look transparent and you'll be able to see through the object whenever there's a voltage applied. All right, so what we wanted to do next was say, well, okay, so this technology exists. Can we include a very thin absorbing layer and use that as a photovoltaic as well? So we could then control the amount of light, the scattering of the light, and generate power at the same time. And so this is what that device looks like. Again, we've got, in the on state, the light passes directly through. We've incorporated this thin amorphous silicon layer here that could be used to absorb the light. In the off state, you'll see it right here. We've only put the amorphous silicon on one side of the device because this is an experiment and we'd like to be able to have a control sample as well. So that's why we put it on half. And when you do that, then all the light gets scattered. You see the white, as we said there before. So you have, in the on state, you have clarity, and in the off state, you can generate power. You actually generate power in the on state as well. It's just a little bit less. And then in the off state, you also have increased privacy as well due to light scatter. So this is what one of these devices looks like in action. So you can see it flipping back and forth. So it's real time. It's a very fast transition. If you've looked at electrochromic devices before, they usually take a minute or two to transition. So it's a very, very fast operation as well. Well, fast for Windows at least. So then we wanted to see if these could be used for self-powering. So the devices that we've made so far, they don't incorporate PN junctions or PIN junctions, but we just want to see proof of principle. Could you absorb enough light to make a useful photovoltaic device out of it? So we do some measurements here where we look at the amount of absorption that we get inside the amorphous silicon as well as within the other layers. The amorphous silicon is down here, the dark gray, in both the on and the off states. And so once we know how much absorption there is, we can say each of those photons could generate an electron hole pair. And if we collect that, if we collect those carriers, how much current would we get? And so here's the short circuit current density that we would get for different thicknesses of this amorphous silicon layer in both the on and the off state. And so I guess the general conclusion here is that you can get a couple of milliamps per centimeter squared out of this. So you can put that into a device model using realistic parameters for amorphous silicon to determine how much power you expect to get out. And here, the amount of power you need to keep it in the on state is less than 1 milliwatt per centimeter squared. And so in all states for both thicknesses, whether it's on or off, there's enough power being generated to sustain the self-powering. So it could keep itself in the on state, or if it's in the off state, it's providing more power, so you could charge your cell phone or something like that if you want as well. Okay, so that's one application of these polymer dispersed liquid crystals, and we wanted to see if there was some other types of applications that we could also use this for. And so here I'm going to step back for a minute and talk a little bit about what a photon is again. And so we know that it's a bundle of energy. It's also a bundle of momentum. And so what that means is each photon has some momentum associated with it. So Planck's constant over the wavelength, h over lambda. And so if it has momentum, that means if it's reflected or absorbed, it's going to transfer that momentum. And if you have a change in momentum, that means a force. Right? So you can have a force exerted. So suppose you have this photon coming from the left towards the right, and there's a mirror here. So what's going to happen is it's going to be reflected off that mirror, and so now the photon is going to go in the opposite direction. So it originally had momentum going to the right, now it has momentum going to the left. Now to conserve momentum, that mirror has to pick up some momentum going to the right as well. And so that's exactly what happens. So for conservation of momentum, that reflection causes the mirror to move to the right. Similarly, we could have a photon just be absorbed inside say a glossy mirror. In that case, we would also have momentum transferred, and there would be, it would give the mirror a kick to the right as well. However, the case on the left here, there's more momentum transfer because in the final state, the photon is going in the opposite direction. So you can actually calculate pretty easily what this force is. So the force is related to the reflectivity and the absorption of these materials, the incident power, and then the constant here that's 1 over the speed of light. So if you calculate what that is, so my laser pointer here is probably a few milliwatts. And so you can have, for something about this amount of power, there's a little bit less than 10 picowatts. 10 piconewtons of force exerted. So I'm exerting a force on this slide right now, on this projector screen, but it's very weak. It's a very weak force. However, if you have a weak force, you also have a weak acceleration. And if you have acceleration, you can, over time, get up to high speeds. And so that's where this concept of a solar sail comes in. So not a solar cell like we use for photovoltaics, but a sail, like a boat that you would have on the ocean. So, for example, when you have a traditional wind sail, you've got this flap here that catches the wind and will push the boat forward. So we can do the same sort of thing with photons if we want. So here, if we have these photons from the sun, they're bouncing off a thin reflective foil in space, and they're transferring momentum to this thin reflective object and propelling it forward. And so that's the concept of the solar sail. And I'd like to just give a one slide kind of background as to where this comes from. This is a concept that's been around for a long time. And so some of the earliest discussions of this, there were back in the 1920s. There's actually a little bit before that as well, more sci-fi stuff, but this is a pretty nice example. Where they talked about having these tremendous mirrors that are very thin sheets that use the pressure of sunlight to attain cosmic velocities. And so it sounds kind of literary and poetic, perhaps, but the idea is that you can just get to these speeds that are really great, so some reasonable fraction of the speed of light just by using the radiation pressure. So kind of a cool sci-fi idea, but it took many decades. It wasn't really until the 1970s until people started thinking about, could you actually use this as a space technology? So there were some studies in JPL in the 1970s, and then things lay dormant until about 2010, when both NASA and the Japanese space agencies both made their first launches of solar sails. And so these were just demonstration missions where they took a sail, they put it up into space, and they opened it up just to see that they could do that, but it didn't go anywhere. So these were just to say, hey, can we put one of these objects up in space and open it out? Since then, private companies have also, private organizations, I should say, have also been involved in doing deployment. So this is the Planetary Society. Again, same idea, they put it up, opened it up, and then let it fall back down to Earth. And NASA is working on one that they hope to have out next year that will actually be the first solar sail that actually does something useful, meaning that it goes somewhere and takes some measurements. So they're planning to send this, it's a NEA Scout, which is near Earth asteroid. So we're going to go to an asteroid, take some measurements, and then send back the data. And so you might have also heard about this other research direction called the Star Shot. And so this was proposed a couple of years ago using a very high-powered laser and a laser sail rather than a solar sail. So same sort of physics, but a lot of very different physics problems, because these are very high-powered lasers that you will use for a very short amount of time to accelerate to 20% the speed of light over the course of 10 or 20 minutes. So a different set of technical challenges, but a similar sort of concept as well. All right, so for the solar sails, which is what I'm talking about today, there are a number of benefits and a couple of drawbacks. So the main benefit is you don't need any sort of fuel, right? So normally that's what limits how far you can go. You need to bring fuel with you, but you don't here because it's just using the sun. You have a small constant force, as I said before, which gives you acceleration, so you can start getting up to very high velocities. Limitation is that once you start going, it's hard to change the orientation of this device, right? Because we're just relying on radiation pressure. So usually what they end up doing is using some sort of mechanical object that you move around the center of mass, or you bring up propellant and you use that to speed and change your orientation. So that kind of defeats the whole benefit of not needing fuel. So one solution is to use something where you can change the reflectivity and hence the radiation pressure. And so, as you may have guessed, we're going to use the types of devices I showed you previously. and do exactly that. So the way that works is you have the force, the light comes in, it reflects off of this thin metal layer, and it will push it forward. If you make half of it transparent, shown over here on the left, then the light passes through that side, but it still exerts a force on the right side, so it'll start to rotate the object. And so you can do that for both directions, obviously, in order to control it. So we've made measurements on these devices. I'm going to kind of skip over some of these details for the sake of time, but just to show that you basically need to measure the amount of light flowing through the object and then what the different orientations of it are in order to calculate how much radiation pressure you would exert on these objects. So you have direct transmission going directly through. There's the total transmission, so light that's forward scattered, and also some light that's reflected in the backward direction. And so once you do that, you can calculate how much momentum is transferred to this device and how much it changes between these two different states. And so this is the solar spectrum here that we're looking at. We made measurements over between 70 and 80% of the solar spectrum and looked at the switchability there. And we found that we could basically have about a half of a photon of momentum change between these two. And so that might sound kind of abstract, but really what this is telling us is that this is a possible technology that could be used to actuate the solar sails in the future. And so the next thing we need to do is say, well, this is a piece of glass, so it's pretty rigid, pretty heavy. So we'd like to see if we can make these things thinner, lighter. So the first thing we did was looked at changing the thickness of this intermediate layer. And as you might expect, these were the first devices we made. As you go thinner, the scattering state doesn't scatter quite as much, and the transparent state stays about the same. It actually gets a little bit better. So you lose a little bit on the amount of switchability that you get. It's a little bit less. But you actually save a lot on the amount of power and the voltage you need. So if I look at how much voltage it requires to turn this device on, it's about 70 volts on these original devices. However, if you go down to about 10 microns thick, you're down to about 10 volts. So you get almost an order of magnitude improvement by going thick. Similarly, the power also is reduced. And as I mentioned before, the amount of switchability is also reduced. However, it turns out that we were working with NASA to do a trade study on this. It turns out that thinner is better in this case. So even though we don't have as much switchability, the benefit that we get by having less weight and less power consumption is worth it. So we wanted to go to more flexible ones. So here's an example of a flexible one on a plastic substrate. So you see you can still get the switchability that's desired, and it's flexible. Now, it's only pseudo-flexible, so you can see that this has a radius of curvature of about 5 or 6 centimeters. So it's not too flexible yet. But what we're working on now is using a polyimide. It's called CP1 that NASA uses for their other solar sail applications in order to make them really thin and really flexible. So on the right here, this is one of these devices with the CP1 that we're working on. And on the left here is a picture from one of my visits to NASA Marshall, where they deployed one of these that they're working on inside a laboratory environment. So you can see they're fairly large. The new ones that they're working on are about 4 times this large, so they're even bigger, so you can get kind of room size, and that's a really interesting way to go to far off distances. All right, so I think I've got one more topic here that I want to talk about. So I think we're a little bit short on time, so I'm going to skip through parts of this, but I'm going to start off with the introduction just to give you a little bit of background, and then I'll just kind of move on to the final results here. So first I'll start off with an analogy. So it's been observed that if you have boats out on the ocean, they sometimes start to get close to each other and collide, even when you don't want them to. And so this was pointed out by people at sea, that if you have rough ocean waves, sometimes these boats have this kind of mysterious attraction that will hold them together. And so I'm going to use this as an analogy for this next effect. And it's not a complete analogy, but it works pretty well. So again, to understand the boats, you can think, well, there's a lot of big ocean waves on both sides, but in between it's relatively calm. So there's more kind of waves outside that push it together and causes them to collide. So we're talking about photons now. So let's go back to thinking about electromagnetic waves. And if we're in empty space, we have, let's say there are no photons here, But if we want to describe what photons would be like, we can look at Maxwell's equations, right? So Maxwell's equations are perfectly valid in empty space. And if we want to treat them quantum mechanically now, we have to quantize these equations. And so this is, if you're used to doing that in, say, an introductory quantum mechanics class, you say, well, what kind of solutions do we normally have here? Well, Maxwell equations, they give you simple harmonic oscillator solutions, so sines and cosines. And when you quantize a simple harmonic oscillator, you end up getting energy states that look like this. So reduced Planck's law, so Planck's constant, h bar times omega, the frequency. And then you have some number of states here plus 1/2. And so what that means when you have a simple harmonic oscillator, that the minimum energy of that state, it's no longer 0. So like your state here is 0, the lowest one. You still are left with this 1/2. And so this is called the 0-point energy. And so Maxwell's equations, if we look at something like that, we say, well, then for quantum electromagnetic systems, we should also have some minimum energy that's not 0. And so what does that really mean? Well, it means we have fluctuating fields that are always kind of existing. And if we were to put boundary conditions on that, you could say, well, between these waves, or between these two plates, if these are metal plates, the fields have to go to 0 on those plates. And what that means then is that there's only certain waves that will fit inside them, kind of like the boats. However, outside, we can fit any kind of size wave that we want. Again, there would be a pressure that would kind of pull these, or push these two plates together. And that's what Casimir calculated. And so it's interesting because it's kind of it's a fundamental physics or electromagnetic problem, but it turns out that there's a lot of real applications for it. So the way in which geckos can climb onto walls, the way that they stick is partially due to this sort of phenomenon. When you have microelectromechanical systems, so small mechanical devices, as they start getting close together, you have to start worrying about some of these sorts of interactions. And also the way that liquid helium can climb out of a container. I don't know if people have seen this, but if you have liquid helium, it will climb out of your container. And it does that for a couple of reasons. So first, it has to be able to flow very well. That's why it's superfluid. But the reason that it wants to climb out of this container is actually due to these quantum fluctuations. It's another kind of interesting point I'm happy to talk to people about later. But anyway, so we've been measuring this force. And so I'm just going to say it's tough. This one slide on this measurement, on the how you do the measurement, it took about 5 years to develop. And I'm going to talk to you about it for 5 seconds, and now I'm done. So it's tough, but when you do it, then you can measure this Casimir force. And so it's a real force. You can see here, there's a calculation here of the full equation for what that should be, and then here is the actual force, and they agree with each other pretty well. And so it's nice to be able to measure one of these forces, but really what we want to do is be able to find some other interesting things that can happen. It turns out that if you look at other geometries, you can not just have an attractive force, you can actually have lateral forces or repulsive forces and things like that. And so those are the types of things that we're interested in looking at. So I'm going to skip over those things, but I'm happy to talk about them if people are interested. And just mention one other thing that's related to that, and that's a torque. So if you had two plates, we had two metal plates originally, we talked about the boundary conditions there, but suppose they were birefringent crystals. So these are crystals where the index of refraction depends on the orientation of the incident light. And so in that case, the boundary conditions on these fluctuations are different depending on what the orientation of these two plates are. So that means that in one case, they're, say, very well confined, in another case, they're not. That means the energy now depends on what the relative angle is between them. And so if you have an energy that depends on this angle, that's a torque. And so it was predicted back in the 1970s that there should be a torque based on this sort of phenomenon. And I will just cut to the chase and show you that you can measure that. And this is what that looks like. So here is a measurement between two birefringent materials. Again, the details I'm happy to talk to people about later if they're interested. But we see that there's actually a sine 2 theta dependence. These are different types of materials that we've used for these measurements. And then we can also look at the distance dependence of this measurement as well. We compare it to theory, and it actually agrees very well with the theory from Barash that was developed in the 1970s. All right, so kind of summing up here, photon is Well, it's the thing that can make a photon detector go click. It's the thing that we could use to propel spacecraft very far away. And it's also something that we can cause forces and torques even when they're not there. So if we remove the photons, we still get some interesting interactions. So with that, I'd like to just conclude and thank our group. Specifically, these students are the ones that were mostly working on the projects that I presented here. Joe Garrett, Joe Murray, Lisa Crayer, and David Summers, and also our funding agencies. And I'd like to thank all of you for your attention today. Thanks a lot.
Thank you, Professor Munday, for this very interesting talk. We have time for a few questions or comments, please.
Yeah, thank you. This talk was great, kind of very interesting. I have a question about solar sails. So I understand that you can selectively absorb to change the
orientation. So I assume that you want to absorb as much light from your light source and repel it as fast as possible. But are there any techniques to like re-radiate in different directions so that you can steer not in line with the light source?
Yeah, no, that's a great question. So there's a couple of different things you can do. So one, you could think about having some sort of reflective or some actively tunable grating, for example. So you could have the light come in, and then as you turn on that grating, you can change the orientation. You could definitely do something like that. And that would probably be most useful for something like a laser-based sail, where you have a particular wavelength that you're interested in. You could also think to do it for a solar application one, but it's more difficult because you have a wide range of frequencies you have to deal with. But yeah, definitely.
Can I quickly also ask on the same point? If the surface is a little bit absorbing, and if you have an intense beam, you risk making a hole in it, right? So is the beam always going to remain diluted enough to offer sufficient force for acceleration?
Yeah, so another great question. So with what we're mostly working with are the solar versions, right? And so for the solar version, that's not as much an issue. For the laser-based versions, it's a huge issue. And so that's why what they're working on, there's actually a number of different parts to this problem. And so let's suppose you get through the first couple of problems, which are getting this super high-power laser that you can get out to outer space. Then if you look at these devices that you want to have be reflecting, it turns out that they have to have much less than 1% absorption. So like 1% absorption is way, way too much. So then it comes down to a photonics design again, where you're saying, can I make a very thin, flexible material that will absorb basically no light? And so you're exactly right. That's one of the challenges, is making something that doesn't absorb any light but reflects a whole lot, basically 100%.
Yes, Jimmy.
So you explained something I had as a kid, it's called a radiometer. It's on a vacuum. There's a shiny side and an absorbing side. So finally, I saw the equation that says you get more momentum, the shiny side and the absorbing side. So that's why it turns. Thank you.
So actually, as a side note on that, so on a lot of those, actually, that's what it's supposed to do. But you'll actually get heating up in some of these. So it's not a perfect vacuum, and so the dark side ends up being hotter, and so sometimes it'll rotate the wrong way. So it's a very interesting little toy because there's some subtleties in it. Yes.
As you know, I always love what carry a solar cell. One of the central challenge there, of course, is maybe a lifetime. Because you generate it, but then deviate it to the expressions of time. Can you explain a little bit about what's the present status, how optimistic you are that we can really expect?
Sure, yeah, so great question. So this was related to the hot carriers, and the lifetime is very short. So I didn't talk at all about the lifetime here. So generally, the lifetime, meaning like how long do they stay hot, is something on the order of like a picosecond or a couple picoseconds at best. And so what that means is you have to be able to extract those carriers before they have thermalized, and then you can no longer take them out. And so for the devices that we're using thin metals, and so the metals are on the order of about 10 nanometers or so. And so the mean free pass of those hot carriers is about 10 nanometers. So for these types of devices, they can make it to that interface that they need to before they've had too many interactions. They basically ballistically travel and can make it over. And so for a hot carrier solar cell device, which is some of the similar physics, but you're usually using a semiconductor, and you want to do in the photovoltaic process line, what it's saying is that you generally need them also to be very, very thin. So you want to make a photovoltaic device that's on the order of 10 or maybe tens of nanometers. And so we started off thinking about that problem as well, but then we were interested in the metals, and so we switched over to there. And so we were thinking of ways that we might be able to incorporate this as a type of photovoltaic device as well, where we could extract hot carriers from it there, and then have a traditional p-n junction device as well. And there's a lot of subtleties that go into that. And we think that we can improve the efficiency of a traditional solar cell using this technology, but details are yet to be seen.
By what percentage is the calculation done?
Yeah, so we think that we can make it more similar to a 2 or 3 junction, so that, like, under ideal circumstances, then you could get maybe about 50% efficiency as opposed to ideally a 30% efficient cell. But once you start incorporating a lot of non-idealities, then you're looking at maybe a few percent sort of improvements.
Any other question? Yes, please.
So there's a lot of energetic particles that are coming out in outer space and stuff. How would that impact
Yeah. Right, another good question. So I guess there's a variety of different types of energetic particles out there. The very small ones are able to pass through without doing too much damage, but there's also a lot of kind of dust-like particles, and those are more problematic. And as you accelerate these sails to faster and faster speeds, then their impact is a lot greater. And so that's something that's being studied right now. There's not like a clear answer. It's something that you definitely have to think about if you're trying to accelerate towards the speed of light and to go to like an interstellar mission. So like the Starshot, that's their plan, is to go to Alpha Centauri, which is the next nearest star. For what NASA's doing right now, it's mostly local. And so for those, we don't reach as high a velocity, so it's less of a problem. Sure. Yeah.
Hello. The force that you're applying, like the solar force, that is like, you saw that it is in the order of piconewtons and all. So I think there will be enough resistance to counter that force. Then how do you create motion if there is like resistance outside?
Okay, so you're referring to the resistance due to like these energetic particles and dust and things like that. Yeah. So there is that sort of resistance, but in outer space, it's mostly vacuum. So that resistance is relatively small. So that is something that is there, but it's these forces are quite large.
So let me ask one last question. So if you send one of our students to Alpha Centauri with this laser-assisted acceleration at light speed, or 20% light speed, how would they come back? They would need some kind of arrangement with lasers there?
Yeah, so that's problem number 52, I think, on the list of problems. But no, there are different groups who are attacking different parts of the problem. And so one thing you have to decide is once you get there, so remember, you're getting there, you're at 20% the speed of light. You're going to zip through that area very quickly. And so what you have to do is you have to take as much data as possible and send it back. So they're trying to devise different chips and processors that you can, and sensors and ways of relaying all that information back. So yeah, that's exactly what you have to do. You have to decide, how do I take the data? How do I send the data back? It's tricky. Yeah.
So there is nowhere you can come back. Seems like you're not asking questions because of that. If there is no other question, let's thank our speaker for this great